I am Harsh Agarwal, an applied scientist at the International Machine Learning Group at Amazon. And this block is about alignment and training. And it's honestly one of my favorites because it's where a raw model stops being a fancy autocomplete and starts being something you actually want to talk to. Let's get started with the help of a question. A pre-trained model can already write fluent text. But here's the obvious thing, right? Like, why can't we just ship that? Like, why do we need this whole block of techniques to be implemented? And the short answer to that is that predicting the next word and being a helpful assistant are just two different jobs totally. And for the next 25 minutes, I would like to walk you through the three moves or the three paradigms that turn one into the other, which is instruction tuning, preference optimization, and synthetic data generation. And by the end of this module, you'll see how each one adds a capability the last one couldn't. So here's the actual problem. The base model was trained on trillions of words with a single goal, which is predict the next token. And it's generally brilliant at continuing the text, but continue the text is not the same as answer my question. If you have a raw based model, and you ask it a question, it might just keep on going with more questions because on the internet, a question is usually followed by more questions. And let me show you the fix for this. As you can see right now, I've asked the model, a raw-based model, the question is, which is how do I reset my password? And it's given me an answer, which is kind of echoing back the question itself. When we SFT this model, it looks something like this. The answer has suddenly taken a shape of the real reply, and it's on topic, formatted, and it's kind of actually helping me. That is what instruction tuning does, and it teaches the format to the model. And when we move on to preference optimization, we can see that the answer is just not any other reasonable answer. It's a better one because it's tighter, safer, and more useful. And that's preferences or human preferences. So across the whole way, there's the same question as to how can we make the response of these models better and better aligned, or like better in terms of the preferences of humans. And it involves three stages of training. And here's the part that I would like you to remember is that pre-training costs trillions of tokens, but each of these alignment steps merely causes thousands of comparisons and thousands of examples, and that's it. Like, the ability is already there after pre-training, and alignment mostly surfaces it. Okay. Moving on to how do we teach the format of helping? And this is instruction tuning or supervised fine tuning. And honestly, it's the simplest idea in the whole deck. And it says that just show it good answers, and the model will copy those good answers. So basically, you're looking at the next word token prediction of a base model. And so I've given the model a question, and you can look at the model's top guesses for next words. They are all continuing either the document or are another question, a bullet point, a line break. But where's the actual answer that we want? It's way down here in the tail, with barely any probability. Don't think that the model is broken, but the model is doing exactly what we have trained it to right now, which is continue the plausible web text or just predict the next tokens. And when we click to translate, basically it's the same story. The top cases just continue to pattern, and there's no uh, and it does not contain the intent of actually answering or performing the task that we're doing. And that's the whole problem right here in this distribution, because the answer stuck down in the tail. And the fix is imitation, wherein you collect a bunch of instruction and ideal answer pairs, and you keep training with the exact same next token loss, which is nothing fancy. And this is SFT for you, and which is done by, so in a primitive way, it is done by using data sets like Flan and Alpaca. And it's really dirt cheap when compared to pre-training. And this step is the one that gives the chart model everyone actually uses. Um, but there are actually two little mechanical tricks that make SFT actually work. The first one is this chart template. So every example gets wrapped in in these roles, which are like system, user, assistant. So the model learns the shape of a back and forth conversation. The second one is actually the important one, which I would like to show you through the image. as you can see, this is one of the training examples and it's in tokenized. And right now we are training on each and every token. And hence every token is being lit up, including what the user has uttered or given the model as input. And think about what that is going to teach the model. Because here we'll train the model to predict the user's prompt also. And in a way, it's learning to parrot the question back to us. And that is not at all what we want. So when we mask the user's input, right, like this, you can see these tokens have been graded, which means they are like they have been dropped from the learning signal, and the learning signal is only flowing through the assistant's reply, and which is ensuring that we are training the model to give the accurate answer or the preferable answer, and that's the sum in the equation only over the answer tokens. This is exactly the same objective as pre-training, and this little mask is the entire difference between predict the text and follow the instructions. So, what does alignment actually mean, and what is the like norm that people are following by meaning alignment? So, people follow this acronym called as HHH, which stands for helpful, harmless, and honest. So, helpful just means that it is going to do the task that you have asked it to do. Harmless is that the model is going to genuinely refuse bad stuff, and honest is the model telling you that it doesn't know something, or it doesn't has that capability or lacks it, instead of confidently making it up, which we also called as the model is hallucinating or showing hallucinations. And there's a and the way to get there is basically a chain. You start with the base model, turn it into a chat model with SFT, and then you align it. And each step adds usefulness. And this is the nice part, that you are never going to retrain it from scratch. But here's the catch. This whole diagram is basically depicting the HHH, paradigm, because every model is going to live somewhere on this space, and up and right is a dream, which is safe and capable model, the which is echoed by this blue dot, and is what good alignment is going to buy you. This basically ensures that there's tons of harmlessness for almost no loss of capability, and basically you just want to keep on increasing this so that you slide towards the right and above as well. Now, but if you do this alignment in a clumsy way, you can go down this orange arrow instead, and or orange head, and that is basically depicting that the model refuses totally reasonable requests, hedges every single answer into mush, and here you have basically traded real capability for little safety, and that's what we called as alignment tax. And honestly, basically the whole deck is about staying around this blue dot, and instead of sliding along, the orange line or the orange dot. So, like, basically, here's the thing about instruction tuning, is that it's going to show the model just the good answers, and it never learns what a bad one looks like. So now we need to teach it judgment, which means learning from our preferences, which is done using paradigms like RLHF, DPO, and GRPO. Now, coming to this question as to why SFT is not enough on its own, because it only ever emits a good answer per question, and it never sees a bad one. So the model cannot learn to avoid, cannot learn what to avoid. And basically, the model right now knows just one path and nothing about the space surrounding it. So RLHF fixes that in 3 steps, and this loop shows the whole flow. Step one is preferences. You show a human two answers and they pick the better one. And notice this is comparing instead of generating the answer, or the perfect answer. And it is so much easier to just say, answer A is better than answer B, than to sit down and write the perfect answer yourself. And that's the entire reason why RLHF is scaling the way it is scaling right now. The second step is reward model. We train a model to score on any answer, fitting all of those human comparisons. The idea is simple: higher scores for answers that people preferred. And the third one is PPO. We tune the model to chase that score. But you can see that this arrow is going back to SFT model, right? And that is the leash. It stops the model from drifting off too much into high scoring nonsense. And hold on to this leash idea because the whole next slide is about why would we need it. So basically, there's a failure of RLHF in real world, and it's called as reward hacking. The reward model is a stand-in for what humans want, and it's imperfect. So if you let the model push too hard, it finds answers that are great on the reward score, but are actually bad. Some of the examples are like padding the answer out, little formatting tricks that the reward model happen to like. And there's a name for all of this, which is called Goodhart's law, which states that the moment a measure becomes the target, it stops being a measure, a good measure. And to prevent this, we have this beta in here, which acts as a leash. And right now, I'm keeping it very low, so the leash is really loose. Let's say at beta equal to 0.02. And you can watch these curves. And the proxy model or the proxy reward model that we are trying to optimize just climbs up and up. But the true quality, it rises, peaks at a certain point, and then starts to drop. Um, and the gap opening up right here, there's the model reward model gaming us because it's scoring higher, but basically responses are getting a lot worse. Now let me increase beta and tighten the leash of the model to, let's say, around zero point 0.3 here. Yeah. So you can see how the model's collapse is pushed back, and true quality hangs near its peak for way longer than we were seeing with less beta. And this is possible because of the KL term doing its job, which is the second piece of the equation and penalizes the model for drifting from where it started. And but there's a catch here that you cannot just crank beta to the maximum known integer, because if beta is very high, the model becomes too tight and it will not improve at all. Hence, a balance needs to be maintained. Also, there are two other things to watch out for: mode collapse, where every answer starts sounding identical, similar to what we observe in GANs. And the second is that the critic going unstable, which is a perfect setup for the next slide. So to tackle these two things of in reward due to reward hacking and in RLHF, we use the PPO paradigm, which is called as proximal policy optimization. And let's explore this. So the equation might look a bit complex, but the idea is absolutely not. Like, all PPO is trying to do is push up the probabilities of actions that were better than expected and push down the ones that went worse. Now, better than expected is the advantage function A, and expected comes from a second network, which is the critic. Now, here's the danger though. One greedy step can yank the model way out to somewhere wherein the estimates don't apply anymore, and then everything goes stale and the training falls apart. The fix is this clipped optimization or objective, and I can show you how this clipping is actually working. So when we look at these good actions or actions wherein the advantage function is greater than zero, basically, you can follow this curve, and we are rewarding a good action more likely, and or like making a good action more likely, and then the rewards, like this objective is increasing with more good and good, and then after one plus epsilon, it just goes flat. And past that point, no more reward is given for pushing harder, and the update literally can't overcome it. Now looking at the bad actions, which is just the mirror image of what we were seeing for the good actions, we push the probability down, but again it flattens at the one minus epsilon uh, point, and so we cannot overcorrect either. And that flat bit is a cheap way to fake a trust region, which is the shaded band here. And epsilon is usually about zero point 0.2, which just means don't change any action's probability by more than roughly 20% in one step. So basically, what PPO does is it has capped like the update to just 20% of the action's magnitude or probability. And this next result is basically like one of the prettiest in the field, because you start from the RLHF optimum, and turns out that the best possible least policy has a closed form, which you can literally write down. It's the reference model times the exponential of the reward. which is normalized with this z of x. And now when we flip it around to get the reward instead and solve for it, the reward turns out to be the just the log of the log ratio of the optimal policy to the reference policy plus a term that only depends on the prompt. So, and here's the magic. You plug that into a preference model from before, and that intractable z of x, it is basically going to be the same for the chosen answer and the rejected answer, so it just cancels out. And what is left is with a loss which is written purely in terms of policy without any reward model anywhere. And this curve shows a really nice side effect. The learning signal is self-pacing. It's biggest when the model's currently uh, where the model's currently ranking a pair backwards, and it fades to zero once the model's comfortably got it right. And so it automatically spends its efforts on examples it's still getting wrong. And you can sample this and see that that's happening here from this image. And coming to the practical implementation of what we've just seen, which is DPO. And because the best policy is linked to the reward by that clean formula, which is log ratio of the policy and the reference policy, best policy and reference policy, you can just fold the reward model into the policy and never build it at the first place, or like never build it separately. And what you're left with is basically one simple loss, which looks much like classification, and basically says that push up the chosen answer, push down the rejected one, and both are being measured by a frozen copy of the model. So there's no reward model, there's no sampling group, and there's no PPO. And let's see how DPO is able to achieve the full job of RLHF or PPO without the complex components. So when we toggle on DPO, you can see that before DPO, the chosen answer and the rejected answer had a close log probability, like log ratio of policies. But after DPO, there's a gap between these two, which what DPO has achieved. And DPO helps to widen this gap, and that's the goal, that pull good and push the bad. And moving to RLHF, RLHF does the same thing, which is widens the gap. And that's the point of comparing them side by side, because DPO got there without a reward model and without the whole RL loop. And that's why it's basically become the default of many model training pipelines right now. And just for knowledge, couple of variants that are worth knowing by name, which is IPO, which is fighting overfitting, and KTO, which is neat because it just works on thumbs up and thumbs down like labels with no matched pairs at all, which is usually how feedback actually shows up in real world. And moving to GRPO, which is behind the recent reasoning models. Remember that TPO needed a critique, right? So, which was like the second big network. And it was just answering one question: was this better than expected? And this is very expensive and it's a pain to keep it stable. GRPO is very simple and just asks that, just says that just ask the whole group. So for one prompt, we sample a whole group of answers, which are these dots that you can see, and we score them. And the dashed line is the group's average reward, and that is our baseline. Answers above the line are the ones that are going to be pushed up, and answers below are going to be pushed down. And it sounds simple, right? And let's resample it again. So you can see that these are the answers that are above the group mean, and these are the answers that are below it, and these are going to be prioritized. And you can resample again and see that the baseline is always going to be the group's mean, and there's no separate critique network anywhere, and the group is its own baseline. And here's why it's perfect for reasoning. The reward can just be a checker. Did like just think of it as unit test cases, like for the code, like did the code pass these unit test cases for a mathematical question, whether the answer is right. So you don't need a reward model. This is literally what the DeepSeek R1 reasoning is trained upon. And it is simpler than PPO, which is because it has no critique and it is online, unlike DPO. And basically, GRPO is PPO with the critique deleted. Um, that is how it is related because it has the same clip objective from the slide of PPO that we saw, and we keep all of that. The only thing that changes is where the advantage number comes from. Instead of a value network, we grab our group of answers and score each one of them and standardize within the group, subtract the mean, and divide the spread, and you're done and dusted. The full objective just averages that clip term over the group and adds the same KL leash we've been carrying on whole time. And here's the payoff in terms of raw engineering. Because for RLHF, with PPO holds four models in memory at once, which is policy, reference, reward, and critique. And GRPO is going to delete the critique model. And if your reward is just a checker, you delete the reward model too. So you go from four networks down to two. That is like halving a huge part of why training these reasoning models become actually practical, and you're saving a lot on the compute costs. And let's have an overview between PPO, DPO, and GRPO. So PPO is the most powerful and most general paradigm. And look at the number of moving parts that it has. It has the reward model, it has the critique, it has basically sampling loop, and it is has the most stuff to tune and the most stuff to break. DPO, on the other hand, is offline. It has no critique, and it just has preference pairs and one closed form loss. There's no reward, there's no critique. And it is if you've got static preferences data sitting there, this is the default that you should do. GRP is online and with no critique again. The group average replaces the value network, and it really shines when your reward is checkable or verifiable and works for components like domains like math, code, or anything to do with a right answer. And here's the thread that I want you to see from this table, that every step removes a component. PPO got four networks, GRPO is down to two, and DPO skips the RL loop completely. And the whole field is drifting towards simpler RL with outcome rewards, which is like just pass the test and get the reward. That's the direction. So everything up to now has leaned on human labels, and that's another bottleneck that we'd like to go after next. But first, let's talk about the bridge, which is constitutional AI. And the problem simple. RLHF leaves huge amounts of human preference labels, and those are slow, expensive, and annoyingly difficult to generate because different annotators just disagree with each other. There's lack of coherence and consistency in their answers, and each annotator is going to add his or her own bias. So like minimization is an important part of labeling here. So what constitutional AI does is that you give the model a short constitution, basically a list of principles that you score on or that are important to you, or basically the list of preferences, and then follow the loop here. The model is going to critique its own answer against those principles and rewrite them, and then the human judgment was just captured once at the starting in the form of principles instead of every single example. And that is why this whole loop is marked as no labels or no human labels. And RLAIF takes it further. So using an AI and not a human to say which answer is better. And RL from AI feedback cuts the labeling cost through the floor, and it loops and then rewrites new training data, so the model gets more harmless with each round without you hiring more labelers or annotators. And this is really the hinge of the whole deck because we are about to take the human out of the loop entirely. Which brings us to this third part, which is removing the human bottleneck through synthetic data generation and self improvement. That is, models that make their own training data. So as we know that human data is the scarce ingredient, and the whole game is become of letting the model generate its own data. But we need to keep a filter so that we just have the good stuff. And I would like to talk about these three techniques that you can actually drive each one for this flywheel of synthetic data generation. The first one is self-instruct, which is very simple, wherein you seed where you take a handful of human tasks as a seed, and the model bootstraps thousands more, and then you just deed up and keep the good ones. Then you spin it and watch the data volume and the quality of the model become both climb the loop. And uh, basically, an anecdote is that Alpaca was built this way. The next one is evolve instruct, wherein you take an instruction and ask the model to make it harder, deeper, and more constrained. So you're literally manufacturing difficulty on purpose. You spin and the quality climbs up again. The third one is called a star, which we'll dive deep into the next slide. But the crux here is that star is going to generate reasoning for filtering and keep what's correct in terms of reasoning. But the whole point here is that the filter is this thing stopping this flywheel from amplifying the model's own mistakes, because a better model, a better data set would hold only if this filter holds. And if you take this filter away from this pipeline, we're just laundering errors straight back into training. And this happens because models have these biases in them wherein they rank their generated answers better in a better, like above the actual preference, or like above the answers that were generated by the model. So this is a egocentric bias that these models have. And hence this filter is really important. And when you see, you just spin the flywheel, the data quality is going to rise and the data volume is going to rise. Um, Diving deep into what star is. So star is the sharpest version of that flywheel, and it basically forms the seed or crux of every modern reasoning model. The problem it solves is of step-by-step reasoning, because this step-by-step reasoning data is really scarce, and humans almost never write out their full chain of thought, and paying them to do this is pretty expensive. So star says let the model write its own reasoning on problems where we already know the answer. So the model drafts a bunch of reasoning attempts, and then there's a filter to keep an attempt only if it landed on the correct answer, and everything else is going to just get thrown out. So you can see R1 landed on the correct answer, and hence it's included in the training set. R2 landed on the wrong answer, and hence it's not present, and so on and so forth till R8. And all of these survivors are going to flow into the training set. And there's here's the clever bit. The thing playing the role of human labeler is just the answer key here. So correctness is a free and automatic label that you get with this answer key, and nobody grades the reasoning itself. We just check whether we got the terminal answer right or not. So there's no step by step or component wise, scoring. It is just the terminal reward or terminal answer that we are going to look at to see whether the reasoning step was fine or not. And there's another trick here which is called as rationalization, and which says that for the reasoning drafts that the model got wrong, you just hand the answer as a hint and let it re-engineer the COT steps backwards to justify it. And we are going to keep those trajectories as well through this, and this helps basically to keep the diversity and like hinting the model to correct what it got wrong also. And if you notice this is exactly like GRPO with a checker reward. To conclude, star is the seed of the RL trained reasoning models that we have in the modern uh, AI system. And so let's close this whole deck by pulling the whole arc together and recap all the three different paradigms that we saw. So instruction tuning taught the model the format of helping and imitating good answers uh, by masking the user prompt also. Preference optimization taught it judgment. RLHF learns the reward and chases it. DPS gets the reward model. And GRPO drops the critique also. These are comparisons with PPO, and the synthetic data generation flywheel took out the human bottleneck itself. And the flywheel is like generate the data, filter the data, and let the checkable tasks grade themselves. And there's one thread through all of these three, and it's that alignment is going to get more automated, and it keeps getting more automated. There are fewer human labels and more model generated in the data set, and more self-verified signals at every stage. So where does this leave us? We've got an aligned model now, or know the techniques that are needed to get an aligned model. The next question is how we are going to actually use it and serve it. And techniques like prompting, adaptation, retrieval, running it efficiently are going to come to our rescue. And that is what the next part of the Gen AI and LLMs module is going to be about. So I'll conclude this module here and thank you. I am Harsh Agarwal, an applied scientist at the International Machine Learning Group at Amazon. And this block is about alignment and training. And it's honestly one of my favorites because it's where a raw model stops being a fancy autocomplete and starts being something you'd actually want to talk to. Let's get started with the help of a question. A pre-trained model can already write fluent text. But here's the obvious thing, right? Like, why can't we just ship that? Like, why do we need this whole block of techniques to be implemented? And the short answer to that is that predicting the next word and being a helpful assistant are just two different jobs totally. And for the next 25 minutes, I would like to walk you through the three moves or the three paradigms that turn one into the other, which is instruction tuning, preference optimization, and synthetic data generation. And by the end of this module, you'll see how each one adds a capability the last one couldn't. So here's the actual problem. The base model was trained on trillions of words with a single goal, which is predict the next token. And it's generally brilliant at continuing the text, but continue the text is not the same as answer my question. If you have a raw base model, and you ask it a question, it might just keep on going with more questions because on